How's everybody doing? I'm doing pretty good. Turn that music down a tiny bit. There we go. Okay. Yeah, I'm doing well, and I hope you are too. I've got some stuff for us to do today. Oh, I forgot. I've got a big me now. I got to put that on my. Well, I've got a second here. We'll throw that onto my stream deck so I can actually get to it when I want to. Okay. Yes, I hope everybody's doing well. We've got yeah, there we go. Cool. See, we've got a couple things going on today. But what I'd really like to do is look at some Bitwise operator stuff. I'm looking at my top screen here. Because I don't want a heavy morning. So we're going to read an article about Bitwise XOR, which if you remember yesterday, we did a bunch of like, can AI do this? With some geez, I lost my train of thought already. It's like we fed it in the 1 billion row challenge and we asked it to explain what was going on. And it didn't do a great job of that. I mean, it did some stuff okay, but it wasn't what I wanted. I wanted a much more in-depth explanation that was actually linked to the specific code examples of the code that I had given it. But that's kind of what we expected would happen. So we did that on Quick Response, we did that on Think Deeper, and we did that on Deep Research, all with Copilot. And you can see that in yesterday's VOD, where we took the response from the AI, we threw it into our notes. And sure, that's a little bit of, I'll call that study for what we're trying to do here, which we're trying to improve how we can do I/O. But one thing I think that we can take from that example already and start looking into is their use of the XOR operator to do comparisons on strings. So when we're looking for things like new lines, which I think is going to be something very important, but when we're trying to isolate any character really, if we can isolate that character using a XOR, it's going to be a lot quicker than trying to actually compare the characters themselves. And we're going to have to do a lot of this character detection when we're doing the reading. So this seems like a pretty good thing to get familiar with. I'm gonna have to like organize my notes later, but so yeah, yesterday here, this is kind of what we went through yesterday. This is the thing we're going to look at here in a second. But we went through the 1 billion row challenge with Copilot, and you know, we got our 3 responses over here. The last one was really the only good one, but today we're going to look at that XOR trick, which is what we have up over here. So let's yeah. Let's take some notes on that XOR trick. Maybe we'll try some XOR stuff ourselves here in a little bit. So, yeah. I think I'm going to switch these windows, though, so that you guys don't have to look behind me in the chat and stuff to see what's going on. We'll zoom in a bunch here, too. Okay. So, let's get going here. Am I ready? Hold on. I gotta move a couple things here. 1 second. We are just about ready. There we go. Okay. Cool. So, there are a whole bunch of popular interview questions that can be solved in one of 2 ways, either using common data structures and algorithms, or in a sensible manner, or by using some properties of XOR in a seemingly hard to understand way. So this is true. Okay, I need less music right now. There. I think it's okay for you guys, but for me it's really loud. Okay. While it seems unreasonable to expect the XOR solutions in interviews, it is quite fun to figure out how they work. I agree. As it turns out, they're all based on the same fundamental trick, which we will derive in a bottom-up way in this post. Afterwards, we will look at a bunch of applications of that XOR trick, such as solving this popular interview question. You are given an array of n-1 integers, which are in a range of between 1 and n. All numbers appear exactly once except one number, which is missing. Find this missing number. Of course, there are a number of straightforward ways to solve this problem, but there is also perhaps a surprising one using XOR. XOR is a logical operator that works on bits. Let's denote it by, I believe that's a caret? Let's find the actual name of the character. Is it in this? I don't even think it is. Thanks, Google. Because honestly, I just cheat and call it an uptick, but I don't know if that's actually what it's called. Wikipedia must have it, right? No? 7? Caret. Okay, so I was right the first time. Yeah, it is a caret. Cool. I was right the absolute first time I guessed. Let's denote it by caret. So let's if the 2-bit it takes as input are the same, the result is 0, otherwise it is 1. So if x equals x, XOR 0. If x equals y, XOR 1. Now, this part I did know, but one thing I've found over time is that taking notes helps solidify concepts. So we're going to be reading things out loud, we're going to be reading them back in our heads, and we're going to be typing them out, and we're going to make sure that we fully understand this so that we can move forward. So, like, even things like writing out this is a caret, how it works, this may not help you, this helps me, like, ground the concept into my brain and, like, fully understand it. You'll also see me from time to time, I'm probably going to pull this up. Actually, I should get it up right now. This is the crap drawing. This is where I draw stuff out to make sure that I actually kind of can think about it in a way that makes sense and actually organize it somewhere not in my mind. Because just because it makes sense right here, if I can't organize it in another way, I probably don't have a full understanding of what it is. Like, I need to be able to manipulate it at least a little bit if I understand it. Otherwise, the result is 1. That's what we did right here. This implements an exclusive OR operation. Exactly one argument has to be 1 for the final result to be 1. We can show this using a truth table. Okay, I kind of want this. I want that truth table. Okay. Okay, so let's refine these notes. And again, this is me researching and taking notes that help me, and hopefully it helps some of you as well. We'll call this background, maybe. We're not going to spend too much time thinking about words because I can clean up the notes later. XOR is represented by a caret. It is an exclusive OR operator. Okay. given input 2 bits. If they are the same, they will XOR to 0. Otherwise, XOR to 1. And then now we can just add the truth table of X, Y, and then X XOR Y. 2 probably. One, two, three. Doesn't it like, do I need to space these out? Okay, hold on. We can just do it this way anyway. We'll just add a table. Insert table. X, Y. Row, column, add to the right. Okay, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. Cool. There we go. Okay. Got it. Most programming languages implement caret as a bitwise operator, meaning XOR is individually applied. Wait, most programming languages implement XOR as a bitwise operator, meaning XOR is individually applied to each bit in a string of bits, e.g. a byte. For example, 0011 XOR 0101 is 0100. Okay. So let's or basic example. So 0011 XOR 0101 equals, it's applied to every bit individually. Okay, so and now we get the proof here. And again, if you're someone who struggles to remember a lot of this stuff, I highly recommend just typing it out. Because not only will it familiarize, like it sounds kind of silly to just say, well, yeah, just type it out. But what I find is that the muscle memory is actually quite huge. So I find just doing this stuff, it gets me thinking in a different way. Like, I'm used to thinking while I'm typing, right? So if I read something technical like this and I'm not typing out some of it or trying some of it while I'm reading it, I'm not going to absorb it because I'm not thinking while I'm doing the task, which is where I'm going to be in the real world when I'm doing this, right? I'm going to be actually typing and thinking at the same time. Because of this, we can apply XOR to anything, not just booleans. That makes sense. Okay. deducing some useful properties. We can derive a bunch of properties from the previous definition. Let's go through them one by one and then compose them to solve the interview question previously mentioned. XOR and 0. If one of the arguments to the XOR is 0, then the remaining argument is the result okay. So I think this is where we're gonna okay. Properties to remember. If one argument is 0, the other argument is the result. Okay. That makes sense. And it makes even more sense when you think of it that way. This directly follows from the truth table by checking the rows where y equals 0, namely the first and third row. So 0, this is 0, so that's the result, right? This is 0, that means it has to be 1, if the other one is 1. XOR on the same argument. If the two arguments are the same, the result is always 0. So if both arguments are the same, the result is 0. So, and again in our truth table, what do we learn? 0, 0, 0, 0, 1, 1 is 0. Intuitively, this means that if we apply the XOR to the same arguments, they cancel each other out. That's a good way of thinking about it. They cancel each other out. Commutativity. Okay, so XOR is commutative, meaning we can change the order in which we apply XOR. To prove this, we can check the truth table for both X XOR Y and Y XOR X. Right, so the order doesn't matter because we're only talking about two things, right? And if they're the same, it's going to be 0 no matter what. If one of them is 0, the result's always going to be the other one, and that's not going to matter which order we do it in. And again, if they're both the same, they're both the same. The order in which the arguments are applied, XOR does not matter. Is okay. Sequences of XOR operations. By combining all of this, we can deduce the central insight behind everything that is about to follow. Okay. If we have a sequence of XOR operations, A XOR B XOR C, so on, then we can remove all pairs of duplicated values without affecting the result. Okay. Commutativity allows us to reorder the applications of XOR so that the duplicated elements are next to each other. Since X XOR X is 0 and A XOR 0 is A, each pair of duplicated values has no effect on the outcome. Okay. Okay, I need to Okay, so that... We're gonna get to that, hold on. Hold on, I have to think of this differently or it's not gonna work for me. Okay, so... Let's... By combining all this, we can deduce the central insight behind everything about the... Okay, so we have a sequence of XOR operations, then we can remove all pairs of duplicated values without affecting the results. Okay. In a sequence of XOR operations, pairs can be removed because they will cancel each other out. Okay. Fair enough. The operations can be reordered to put duplicate values to each other and thus canceling them out. Okay. Let's XOR sequence example. Let's say we have A XOR B XOR C XOR A XOR B. So because caret is a bitwise operator, this will work regardless of what kind of values A, B, and C are. The idea is really at the heart of how XOR can be used in seemingly magical situations. Okay, so this is the same as this. A XOR A XOR B XOR... Oh. A XOR A XOR B XOR B XOR C, which is the same as 0 XOR, which is the same as 0 XOR 0 XOR C, which is the same as C. Right. This works regardless of the actual values of A, B, and C. Okay. So now that we've got a quick background and we have some things to remember here, let us jump into in-place swapping. Okay. Before we solve the problem of finding the missing number, let's start with this simpler problem. Swap two values x and y in place without using any helper variables. It turns out that this one can easily solve this problem using the following three XOR instructions. A XOR Y, XOR equals Y, Y XOR equals X, X XOR equals Y. That seems a bit mysterious. Why do we end up swapping X and Y if we do this? Okay, so let's swap two values without using a helper variable. So we're going to make this electrical applications. Okay. Cool. So let's use this to swap some variables. No, that's not what we want. This should be whoop. Whoop. Okay. So see how it works. Let's go through this step by step and comment each instruction. Okay. So this is what we get here. We can see that this is really just using properties we derived earlier. The fundamental insight here is that having XOR Y in one register and X in the other allows us to perfectly reconstruct Y. Once XOR Y is stored in instruction 1, we can just put X into the other register, instruction 2, and then use it to change XOR Y to just Y, instruction 3. So XOR equals is similar to plus equals then. You okay, so let's come back up to here. We'll do that later. Okay, so let's okay. We've got X XOR equals Y. Which would be so let's, I guess, X equals 0, Y equals 1. So this is going to equal the XOR of that, right? And the XOR of that is going to be 1. And then we add Y, right? And then next we're going to say Y XOR equals X. Okay. And here Y is equal to 1. And then it's going to add XOR Y, which I believe it now X is 1, 1, right? Right, XOR Y. So then wouldn't we end up with okay, maybe I'm not understanding this then. Okay. Okay, stores the result back into the left. Okay. Okay, so it's not actually... Okay, so... Which is... So... X was 0, now it's 1. And then... Okay. Okay, so this is going to be... Now we have this as XOR Y, so we're not... We'll break this out in a second. And now... This is... So, XOR Y. This notation is confusing me. I don't understand what I'm looking at. Current values... Okay, the current values of X and Y. So this is X. And this is Y. Right, okay. So... Okay, so I'm going to represent this differently then. Then we're going to say X equals XOR Y. Y equals Y. And then down here, now we have X equals XOR Y, and Y equals Y XOR XOR Y. Let's see if it... Okay, yeah, this will highlight it nicer. There we go. Okay, so now X XOR equals Y. We've got X equals X XOR Y XOR X, and Y equals X and then that's really going to reduce down to Y because the two X's are going to cancel each other out. Right? So X equals XOR Y, and then in this case now Y still equals Y. So when we do Y XOR equals X, we know X is still equal to XOR Y, and Y is now equal to Y XOR Y. So these two are going to cancel out to make X. And then, yeah, so down here we can say the first, we'll do this in point form so that I can actually understand it later. In the first instruction, X becomes, wait, yeah it does, okay, it becomes X XOR Y. Second instruction, Y becomes Y XOR Y XOR X, which reduces down to X. Third instruction, X becomes X XOR X XOR Y, which reduces down to Y. Clear as mud? Okay. So okay. Having X XOR Y in one register and X in the other can be used to reconstruct Y. Y. So once we have this, we can use that to make Y, which, okay. I'm trying to understand how the way they're wording it might actually be different. Here, one sec. I wish I could make it so these don't show up here. I was trying to figure out if I had any Chrome tabs open, but I don't because I'm using Firefox. Yeah, I think it's just I don't think there's anything really to glean other than what I've already said. I don't think there's any extra insight. I think it's just a more wordy way to explain this. Having this in one register and X in the other, I don't see where X is in the other, because like at this point X is we never have X in the other register though, I guess is kind of where I get confused with what he's saying, because when I do this, X becomes X XOR Y. So I guess he's saying that once I do this, I have X in the other register. Once I do that. So I think I understand it. I think I just don't like that wording, which is fine. I don't have to like it. So now we're going to jump on to find the missing number. Okay, find the missing number. So let's finally solve the problem posed at the beginning of the post. You are given an array of A. You were given an array A of n-1 integers, which are in the range between 1 and n. All numbers appear exactly once except for 1. Find the missing number. Okay. You are given an array let's call it A. A contains n minus 1 integers, which all range between 1 and n. Okay. That's not what we want. We want this. Okay. All numbers appear in the array exactly once, except for one which is missing. Find the missing number. Okay. So, of course, there are many straightforward ways of solving this, but we did set out to do it using XOR. From the XOR trick, we know that having a sequence of XOR statements mean we can remove all duplicate arguments. If we just XOR all the values in a given list, however, we cannot apply this trick because there are no duplicates. Note that a n-2 is the last index of the list of n-1 elements. What? Note that n-2, right, because it's 0 indexed, and there's n-1 elements, yeah. What we can do additionally is to also XOR all values between 1 and n. This will give us a sequence of XOR statements where elements appear as follows. Okay. Let me think about that for a second, and then we'll re-go through that again really quickly. Okay. From the XOR trick, we know that having a sequence of XOR statements means that we can remove all duplicated arguments. If we just XOR all values in the given list, however, we cannot apply this trick because there are no duplicates. What we can do additionally is to also XOR all values between 1 and n. This will give us a sequence of XOR statements where elements appear as follows. All values in the given list now appear twice. Once from taking all the values between 1 and n, once because they were on the original list. Okay? The missing value appears exactly once. Once from taking all the values between 1 and n. Got it. Okay. If we XOR all of this, we essentially remove all values that appear twice thanks to the XOR trick. This means that we are left with the missing value, which happens to be exactly what we are looking for in the first place. Okay. Let's take some time and really absorb that. Okay? So, A and n. 1 to n plus 1. So XOR all the values from 1 to n, XOR all the values in the array. Right. So I guess it's because order doesn't matter. Okay, so XOR all of the values between 1 and n. So that's going to be 1, XOR 2, XOR 3, XOR 4, XOR 5, XOR n minus 1. This will give us a sequence. This is a sequence so XOR of all of the solution, which contains all elements between 1 and n minus 1. Okay. Okay, and then apply the result of that XOR to the array. We'll call that L. And then we'll say L XOR A 0 XOR A 1 XOR A 2 XOR A n minus 2. All of the integers that exist in both the reference list and the array will be canceled out, leaving only the number that was missing. I believe this is Python. Ooh. Okay. We'll fix this. Hold on. There we go. Okay. So now let's maybe take some time and maybe try to do this in Java. See if we can get this. Just going to Okay. So. Okay, so we are going to have an array of integers. Let's do 5. So that means I didn't. Okay. Sorry, I'm thinking here and I'm looking at stuff. Okay. What do I want to do here? Okay. Please hold. Oh, I know what I want. I want this. Or no? Why broke? Okay, I'm gonna lose my mind if this doesn't match title, otherwise same type of executable. Is that it? Does that work? Okay. Ah. There we go. Okay. Why are you just like a tiny bit too big? What? What is... Why? Okay. Sure. I don't know why things the way they do. They just do. Okay. Please hold. Please hold. So let's get into this. Okay. So this is going to be, we said 5, so we're going to do this. And we need a missing number. So we're going to be missing 3, and then we're going to say the reference list is 1, 2, 3, 4. Right? And then now we have to XOR the reference list. So int result. And so start it at 0 because 0 always becomes the argument beside it. Or wait, we should be doing reference first, right? So this is going to be reference. And then XOR equal I. What do we get? We just pushed the wrong button. 3. Hey, it works. Okay. That's cool. Okay. Give an array. Let's mark this up a bit. Missing 3. The reference list. The results. XOR the reference array. Apply. So now this result equals 1 XOR 2 XOR 3 XOR 4. XOR the input. So now we've got 1 XOR 2 XOR 3 XOR 4 XOR 1 XOR 2 XOR 4. Which is gonna, I can't, okay, so now we're gonna have to which means result equals 1. Or actually, I guess technically, it's this. Which is technically 0 XOR 1 XOR 1 XOR 2 XOR 2 XOR 3 XOR 4. Actually, you know what? Let's 4 XOR. We'll order them like this. Or no, sorry. It should be XOR 3, result equals 3. And you know what? We can... Okay. Here we go. I think this makes sense. So, let's throw that into our notes. Desktop. Okay, so this is Java. We can do with some less spacing though. Okay, I don't know why it's double spaced, but it is. So we'll undouble space it. There. Cool. I like that. It's kind of cool when you write it out like this and you like actually look at what's happening in the background. Okay, so going back just to make sure that so far this is pretty good. Well, we worked on integers from 1 to n so far. This is not required. In fact, the previous algorithm works in any situation where there is 1. some set of potential elements, and 2, a set of elements actually appearing. The set may only differ in one missing element. The sets may differ in only one missing element. This worked out nicely for integers because the set of potential elements corresponds to the elements from n to 1. One could imagine applications where elements are not integers from 1 to n, of course. The set of potential elements are person objects, and we ought to find the person missing from the values. The set of potential elements are nodes in a graph. We are looking for the missing node. The set of potential elements are integers in general, not necessarily 1 to n, and we want to find the missing integer. Fair enough. So this is an important node, I think. So let's do a call out here. Insert call out note. Beyond integers. This method will work on any type, not just integers, as long as there is a reference list and an input list that is missing one entry. The algorithm seems a bit magical, which I hope it does not. It might help to think about how one could achieve the same results using arithmetic operators. Okay. Okay. Here we go. Using the same principle with arithmetic operators. Okay. We'll take his, and then we'll modify ours in Java, and we'll see how that goes. Because XOR can be oversimplified to cancel out the things that match when working with integers. A similar solution can appear just using math. Okay, I don't know why. What if I do this? Is this going to fix my problem of not being able to do what I want? If I just do that? Yes, it will. But for some reason my VS Code is double spaced, which is fine. There we go. Okay. That's fine. So now, let's do our Java version. So we still got all this, except now we can say plus equals instead, and minus equals. I think this is just going to give us 3. 3. It works. Plus 2 plus 3 plus 4 minus 1 minus 2 minus 4 plus 1 minus 1 minus 1 plus 2 minus 2 plus 4 minus 4 plus 3 equals 0 plus 3 equals 3. Okay. Variable to store the results. Add all reference elements together. Subtract all input elements from the reference. Cool. Okay, copy that. Okay. Fix that up. There we go. Cool. We had all potential integers and then subtracted the ones that are actually appearing. The solution is not as nice, but would need to be... the solution is not as nice because one would need to handle overflows because it requires the type of element to support plus and minus with certain properties. It, however, has the same logic of elements of canceling each other out. Yeah, exactly. So we'll leave a note here. This is not a true one-to-one solution, as this only applies to types where addition and subtraction are present, but logically it is the same. Okay. So this should just be the opposite, I would think, right? I think this is just like the full opposite. Here's where it gets fun. We can apply the exact same solution to a similar interview question. You are given an array of n plus 1 integers where they're in a range between n and 1. All numbers appear exactly once except one which is duplicated. Find the duplicate number. Let's think about what happens if we just apply the exact same algorithm from the previous solution. We would get a sequence of XOR statements where the following would appear. The duplicated element would appear 3 times. Once from taking all the values of n to 1, twice because it's duplicated in the original list. All other values given in the list would appear twice, once from there and once from there. As previously, all duplicated elements cancel each other out. This means we're left with exactly what we're looking for because we had 3 and 2 are going to cancel each other out. The element that was duplicated in the array originally, this element appears 3 times combined with XOR, reducing that down to just itself. Okay. So I guess let's do that one, I guess. Let's do that. using the same principle to find a duplicate. And we are going to put in a quote here. How did I phrase this one? Let's start with this and just modify it. Okay. If you are given an array, let's call it A, that contains n plus 1 integers are all between n, 1 and n. All numbers appear exactly once except for one, which is duplicated. Find the duplicate. Okay, so let us do that. Let's try this one now. So now we're gonna have 1, 2, 3, 3, 4. And then, so theoretically, if I turn these back to XORs, does that just work? Is that just gonna find 3? Yeah. Okay, so now, give an array 3 is duplicate. The reference list, go to results. Okay. So if we do this, we get 1 XOR, 2 XOR, 3 XOR, 4. And 1 XOR, 2 XOR, 3 XOR, 4 XOR, 1 XOR, 2 XOR, 3 XOR, 3 XOR, 4. Okay. So now we can start reducing, which is 1 XOR 1. I guess I didn't need to do that at all. XOR 2 XOR 2 XOR 3 XOR 3 XOR 3 XOR 4 XOR 4, which is 0 XOR 0 XOR. I'm going to reduce this a little bit weirdly, but I want to show what's happening. 3 3 3 XOR 0 0 XOR 0 XOR 0 XOR 3 XOR 0. I know I'm writing this out in a really stupid way, but I feel like this kind of really drives home why it works. Because we can just start shifting things like this, and then now we've got... Actually, let's do... equals that. Cool. So that gets us to there. Okay. If anybody knows why this does double spacing, leave a comment or type something in chat and maybe I can fix it for next time. Cool. All numbers except for 3 are in the XOR chain 2 times. So they cancel out. 3 appears in the XOR chain 3 times. 2 of the 3's cancel out, leaving 1 of the 3's. Okay. That all makes sense? Clear as mud. It turns out we can take that even further. Consider the following slightly more difficult problem. You are given an array of n-2 integers, which are in a range of between 1 and n. All numbers appear exactly once except for 2 which are missing. Find the 2 missing numbers. As before, the problem is completely equivalent when looking for 2 duplicated numbers. I'm sure you guessed it, but we'll stick with what worked before. Start exactly the same way. Consider what happens if we use the previous XOR algorithm. If we do, we end up with a sequence of XOR statements where all elements cancel out except the 2 that we're looking for. We will denote these elements by U and V, mostly because we have not used those letters before. After applying the algorithm, we are left with U XOR V. What can we do with that? We somehow need to extract U and V from this value, but it's not immediately clear how to do that. Okay. Luckily, we can figure out what to do by using what we stated earlier. If the 2 bits XOR takes as input are the same, the result is 0, otherwise it's 1. If we analyze the individual bits in U and V, then every 0 means that the bit had the same value in both U and V. Every 1 means that the bit differed. Using this, we find the first 1 in U XOR V, the position I where U and V have to differ. Okay? Then we partition A as well as the numbers from 1 to n according to that bit. Then we end up with 2 partitions, each with 2 sets. Okay. So, what we're talking about here is I have an array, 2 missing numbers, right? And then we XOR it all against a reference. And that gives us U XOR V, okay? And then find the first 1. And then we'll come down to here. I'll make a silly line. Okay? And do this. There. Okay. And then use index of first 1 to split the original list into 2 smaller ones. Okay. So what happens if we use okay. Luckily, we can figure out what to do by using that. Okay. Boolean a bit stiffer. Partition 1. The set of all values from 1 to n where the ith bit is 0. The set of values from A where the ith bit is 0. Okay. So basically everything up to the 1 and everything 1 and after. Since U and V differ in position I, we know that they have to be different partitions. Now we can use another insight we described earlier. While we worked on integers from 1 to n so far, it is not required. In fact, previous algorithms work in any situation where there is one set of potential elements and two, yeah, exactly. These correspond to exactly the two sets we have in each partition. We can thus search for U by applying this idea to one partition and then find V by applying it to the other partition. I wish that they showed an example of that, but so I do have another. Okay, 1 second. Maybe we'll save this one for another day, but one might try to take this further and aim to solve the problem for more than 2 missing values. I did not give this an abundance of thought, but I think this is where we stop. Succeeding with XOR. Okay. I mean, maybe, maybe not. Now, I do have another one here. Does this show me the 2 missing? No. This is a different thing entirely. Okay. I thought that was pretty cool. So to find the 2 missing, like, I guess the part that I don't understand is like the ith bit stuff. So give me a second here. We'll go to me cam here for a second. Let me see if I can find the example for 2 missing values. I kind of want to go through that. Okay, wow, I found a Java example that's already written. So let's maybe just take the Java example and walk through it. I won't actually write it out this time. Okay, hold on. Let's go to here and we'll say expanding to find 2 missing numbers. And again, this one is not my code. This is by this person, Arnav Mendel. Okay. Okay. So, function to find 2 missing numbers. So, get the XOR of all elements and the reference. So, that's the first part. Now, XOR has XOR of 2 missing elements. Any set bit in it must be set in 1 missing and unset. Wait, what? Now XOR has XOR of 2 missing elements. Any set bit in it must be set in 1 missing and unset in the. I don't like that as a sentence. So XOR contains only. Okay. Let's call the missing values U and V. Everything else cancels. Okay. Get a set bit of XOR. Okay. So this is... Get a set bit of XOR. Okay. Index of rightmost 1. So this is going to be okay, guys, I do have to go. So, you know, I think we're going to can this example. I'll write it out myself. I don't want to have to understand what that guy is doing. I don't like the way it was explained. So maybe later today, we'll see. Maybe another day we'll do the 2 missing ones. But I think this is a pretty good primer into using the XOR operator. But that's all the time I have for today. I will see you guys later. Have a good rest of your day. Do I have an ending screen? I do have an ending screen. Go me.